Welcome to our quantum deep dive. Today, we're tackling a concept you think you know from science fiction, the wormhole. But its real story? Oh, it's so much stranger. And it starts not with starships, but with a puzzle about the very nature of a single particle. We're exploring the Einstein-Rosen Bridge, all based on a fantastic essay by Jörg O. Schneepatt.
So here's our roadmap. We'll kick things off with Einstein's original and kind of surprising goal for this bridge. Then we'll get into why you couldn't actually travel through it, before diving into the spooky quantum connection that gave it a whole new lease on life. From there, we'll look at the wild recipe for a traversable wormhole and see how scientists are now building them on a computer chip. And finally, we'll ask the big one, what does all this tell us about the fabric of reality itself?
Okay, let's get right into it. When I say wormhole, what pops into your head? Probably starships, right? Zipping across the galaxy in a flash? Well, that's not at all what Einstein and his colleague Nathan Rosen were thinking about. Not even close. Their goal was much, much smaller.
See, back in 1935, their paper wasn't about finding shortcuts through space. It was about solving this really deep, kind of nagging problem in physics. How do you describe a fundamental particle, like an electron, without running into something called a singularity?
So what is a singularity? Well, you can think of it as a point where physics just breaks. All our equations spit out infinity, and everything goes haywire. For a guy like Einstein, who is all about elegance and order in the universe, this was a total nightmare. He hated it. So this bridge of theirs, it was this brilliant mathematical sidestep to picture a particle as a smooth little tunnel in spacetime, avoiding that nasty infinite point altogether.
Okay, so they came up with this bridge idea to describe a particle. But here's the kicker, and this is the really crucial point. In the world of classical general relativity, the world Einstein was working in, this bridge is completely, utterly useless for travel.
And this table just lays it out perfectly, right? The sci-fi wormhole is a stable tunnel, waiting for you. The real Einstein-Rosen Bridge, it's the opposite of stable. It's so incredibly fragile that the instant anything, even a single photon tried to go through, poof, the whole thing would collapse into a singularity faster than light could even cross it. So no starships allowed.
So if it just collapses, is that it? Game over? For a long, long time, yeah, that was pretty much the consensus. The Einstein-Rosen Bridge was just a cool mathematical quirk, a dead end. But then quantum mechanics showed up, and things got really weird.
Right. And to really get your head around the modern idea of a wormhole, we have to do a complete 180. We're going to leave the clean, geometric world of gravity for a minute and dive headfirst into the bizarre world of quantum mechanics. And specifically, something Einstein himself famously called spooky action at a distance.
This is the famous Einstein-Podolsky-Rosen paradox, EPR. And hey, notice that R? That's for Rosen, the very same guy from the wormhole paper. Kind of cool, right? So they described this spooky, instantaneous connection between particles. For the longest time, everyone thought these two ideas, wormholes and entanglement, were totally separate things, until, you guessed it, a wild new idea came along and smashed them together.
And here it is. In 2013, physicists Juan Maldacena and Leonard Susskind dropped a bombshell, the ER equals EPR hypothesis. And honestly, this is a stunner. What they proposed is that these two things aren't just related, they are the same thing. They're two different ways of describing the exact same reality. What if that spooky connection isn't just some abstract link? What if it's a tiny physical wormhole, an Einstein-Rosen bridge, connecting those two particles?
And this quote here really just nails it. Entanglement is geometry, non-locality is topology. Basically, it reframes everything. That spooky action isn't spooky at all. It's just the shape, the topology of space-time itself. This idea completely changed the game. It took wormholes from the dusty shelves of theoretical physics and put them right at the heart of the biggest questions we have today.
Okay, so if entanglement is a tiny wormhole, that raises a huge question, right? Could we use that connection to build a wormhole we can actually go through, one that doesn't just collapse on us? Well, theorists like the legendary Kip Thorne had already cooked up a recipe for just that, but the ingredients are, let's just say, they're pretty strange.
So the recipe, which comes from some incredible work by Morris and Thorne way back in the 80s, seems simple enough on paper. Step 1, you start with Einstein's equations. Step 2, you design your tunnel. But step 3,
That's the catch. You have to prop the throat of the wormhole open with something called exotic matter. And we're not just talking about something rare. We're talking about stuff that breaks the normal rules of physics, stuff with negative energy or negative mass. Basically, it has anti-gravity. It pushes space-time apart instead of pulling it together.
Now that sounds like pure sci-fi, I know. But here's the wild part. Quantum mechanics actually says, yeah, that can happen. It's called the Casimir effect. It's a real, measurable phenomenon where you can create a tiny region with negative energy density in a vacuum. Now, to be clear, it's nowhere near powerful enough to hold a human-sized wormhole open. But it's the proof of concept. It shows us that the laws of physics don't completely forbid the idea.
All right, so building a real traversable wormhole is still way off in the future. But what if there's another way? Thanks to that ER equals EPR connection, scientists had a brilliant idea. What if you couldn't build one in space, but you could build a simulation of one on a quantum computer?
And that's exactly what happened. In a massive breakthrough in 2022, a team at Google Quantum AI announced they'd done it. Using their Sycamore quantum processor, they had successfully simulated the behavior of a traversable wormhole.
So let's be super clear about what this means. They did not open a little portal in their lab in California, okay? What they did was create a tiny quantum system with just 9 qubits that behaved exactly like our theories predict a traversable wormhole should. They sent a bit of information into one part of the system and watched it pop out the other side, just as if it had tunneled through. It was this incredible real-world proof of the ER equals EPR idea in action.
And this is where it all comes together. This is the big picture. These amazing experiments and the whole ER equals EPR idea, they aren't just teaching us about wormholes, they're pointing to something far deeper, a completely new way of looking at reality itself.
So here it is, the big question. What if space-time itself isn't fundamental? What if it's emergent? The idea behind ER equals EPR is that the very fabric of space-time is literally woven together by quantum entanglement. All those connections between particles, what if that's what creates the geometry of space? The feeling of close and far might just be a shadow of a deeper quantum reality.
And this isn't just some hand-wavy philosophical idea, there's some serious math backing this up. The Ryu-Takayama-Yu formula gives us a concrete mathematical link. It shows that entanglement entropy, which is basically a measure of quantum information, is directly tied to a geometric area in spacetime. Think about that for a second. It's saying that information is geometry. Entanglement isn't just happening in space. In a very real sense, it is space.
So, when you step back and look at the whole journey, it's just incredible. What started out as Einstein's clever trick to get rid of an infinity in his particle model, a trick that seemed like a dead end for decades, has now blossomed into this incredibly powerful new way of thinking. It's become a symbol for unifying gravity, quantum mechanics, and information theory, the 3 great pillars of modern physics.
Which leaves us with one last mind-bending thought. Are we living in a universe that builds itself from the ground up out of quantum bits of information? A universe where space and time are just illusions, created by an unimaginably vast network of microscopic wormholes connecting everything to everything else? What a ride, huh? From a 1935 paper about a single particle all the way to the frontiers of quantum computing and what reality is even made of. We really hope you enjoyed this deep dive, which was all based on the fantastic work of Jörg O. Schneepat.
Absolutely, and for more, you should definitely check out schneepat.de.
Thanks so much for joining us, and goodbye.
Schneepat.de is a private project by Jörg O. Schneepat dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.